Well, we're about to study rotation, and what I'd like to do in this video is to give you an overall introduction to it, and I'm going to make this parallel the last video, which sort of summarized what we've done with mechanics, so I would hope that you've already looked at that one, because this is going to parallel that one. And here's the basic deal. As I said in the last video, as we've been studying mechanics, we have been looking at things moving. We've been looking at things having velocity and acceleration. And that's one kind of motion. What we have been ignoring up till now is that there's a whole different way that things can move. And that other way that things can move is rotation. So what I'm going to have us do right now is consider a round thing, and I'm going to put a reference line on it. I hope that this is all, okay, good. The smartboard sees that it all is one object. Okay, by the way, we don't have to have round things rotate, but that's just kind of the typical way to start. So I have this round thing, and again, I put a reference line on it. And in fact, so what I'm going to do is I'm going to have it rotate. So here we go. It's rotating. It's not a very good sphere, but I don't care. And the question that I would ask is, gee, is this thing moving? And you can definitely see some sense of motion in it. But it's not moving around the board. It's not translating the way it would if I were to do that. This is, if I move it back and forth across the board, it has a linear velocity, and it also accelerates because this board has built-in friction, which is nice. That's the kind of motion we've been studying so far. What we're looking at now is the fact that, again, this object is staying in one place in terms of its position on the board. The center mass isn't going anywhere, but we definitely see a movement here. We see a rotation. Can we describe this? Can we learn about what makes things rotate? Can we go through the same general trend that we did with mechanics in general? Can we treat rotation the same way? And the answer is yes, we can. And it's really helpful as we study rotation to recognize that we're going to be doing it analogously to how we studied motion in general through mechanics. So we're going to study kinematics, we're going to study dynamics, we're going to study energy, and we're going to study momentum. The key thing with momentum, as we'll get to in a second, is that we're not studying the same quantity that we were earlier. There's actually a whole new quantity called angular momentum, but we'll get to that. All right, so what I'd like to do in this video is to just run through the general approach that we take to studying rotation, and slightly more detail than I just did in one sentence. All right, we will be studying kinematics. And when we study kinematics, we're not going to be studying velocity and acceleration of this thing moving around the room. We're going to be studying the velocity it has by nature as rotation. So this is a slow rotation. This is a faster rotation. And so we will learn to describe those, how fast it's rotating, with a quantity that we're going to call angular velocity, which basically is how many rotations per minute or rotation per second this thing undergoes. The units we'll be using is radians per second because that's the MKS unit for angular velocity. But basically, we're going to have a quantity that's analogous to plain old velocity. It's called angular velocity, and it tells us how fast, slow, fast, and also in what direction. This thing can rotate in two different directions. And in fact, if I allow this thing to rotate in three-dimensional space, it can rotate in lots of different directions. And so we're going to be learning about the magnitude and direction of the angular velocity, how fast it rotates. This thing can also rotate slower, but be rotating faster. It can be gaining angular velocity. That means it has an angular acceleration. And we'll be learning about angular acceleration, the rate at which the angular velocity changes. So our study of kinematics is going to be very similar to our study of kinematics before. So similar, in fact, that we're going to be doing it in all of about 2 days. And we're going to have very similar looking equations. The difference is that instead of plain old velocity, we're going to be learning about a new quantity called angular velocity, which has a different symbol, which is a Greek letter omega. We'll be using a lot of Greek letters. It's just kind of traditional in physics to use the Greek alphabet for rotation. That's why, by the way, you use theta in math class for angles, because theta is a way of measuring how far something rotates. And regular letters for linear kinematics. We also have A for plain old acceleration, or linear acceleration. These are linear quantities, things moving along the line. And we will have angular acceleration, which is abbreviated with a small case Greek letter alpha for angular acceleration. And that angular acceleration answers the question, is something rotating faster and faster or slower and slower? Or even, in fact, is the axis of rotation changing?
Lowry to the main office. Sarah, Lowry to the main office.
Sarah has got to go to the main office. Okay, so that's kinematics, and we will, as I say, do that in a couple of days. That will be followed, just like before, with dynamics. And when we study dynamics with rotation, remember the central question in linear dynamics. The central question in linear dynamics is, if something is accelerating, how do you make it do that? Well, it accelerates because there's an unbalanced force on it, and the acceleration you get is equal to the magnitude of the unbalanced force divided by the object's mass. This is Newton's second law, big deal in dynamics, big deal in physics. Okay, for rotation, we have a very analogous line of thinking. We look at an actual physical object. So this might be a frisbee, or it might be a basketball, or it might be a flywheel, which is a wheel that a fly runs on, or it might be a planet. And we say, oh, it's rotating. If it's rotating at a constant angular velocity, well, the Earth has been rotating at a constant angular velocity, or very nearly constant, for billions of years, and we don't ask what's making it do that. We ask, so the same as we do with linear motion, we don't need to explain something rotating. We need to explain something's changing in state of rotation. We need to say, oh, does it have an angular acceleration? And if so, why? So if you see something going rotating slowly and then rotating faster and faster and faster, you would say, what's making it do that? And the quantity we'll be speaking about is torque. Torque is a quantity that's not the same as force. It's said to be analogous to force. If there's a torque on an object, it tends to make it rotate. That's not quite accurate to say, and anymore, like you shouldn't say if there's a force on an object, it tends to make it move. What you should say is if there's an unbalanced force on something, it tends to make it accelerate. And the same thing with rotation. If there's an unbalanced torque, and the symbol we'll use for torque is this capital Greek letter tau. Remember, we're using Greek letters. If there's an unbalanced, I just misspelled sigma. If there's an unbalanced or a net torque on an object, that means it will have an angular acceleration. So again, torque is like force, not exactly the same quantity though. And there's another quantity we'll be learning about, which is analogous to mass, and it's called rotational inertia, and that's capital letter I. It's probably a Greek I, like iota or some craziness like that. But in any event, we use a capital I for rotational inertia, and that's a quantity that tells you, that describes an object's resistance to changing rotation. Something has a large rotational inertia. If it is hard to make it speed up or slow down its angular velocity. So that's going to be the equation. That, in fact, is still called Newton's second law. This angular acceleration equals net torque over rotational inertia. And that's going to have us studying dynamics. Okay, the next thing we will do, as we did before, is move the page, is we'll study energy. Energy is still conserved, even though something's rotating or not. And we've even referred to this a little bit in class. We're basically going to be adding one more kind of energy to our list of kinds of energy. And the kind of energy we're going to be adding is called rotational kinetic energy, K-ROT. We'll affectionately call it in class. And rotational kinetic energy isn't really a new kind of energy. It still is just plain old kinetic energy. But basically what we're going to say is if you have a rotating object, like this frisbee we had earlier, and if it's rotating in place, okay, a rotating thing rotating in place has kinetic energy. And so, for instance, the wheels on your car, simply getting those wheels to move, even if your car's not going anywhere, takes energy. It takes gasoline to get those wheels to spin. And so those spinning wheels have kinetic energy, even though they're not translating, they're not moving. So this is kind of goofy. So I picked the car up with straps or something, and I've got the wheels spinning in place. And the wheels are spinning around as I gun the engine. And that takes energy to make that mass move, even though it's moving in place. It's rotating. Okay, so rotational kinetic energy is going to be another form of energy we add to our list of kinds of energy. The formula for that will be analogous to plain old kinetic energy. It's going to be 1/2 I, rotational inertia, which is analogous to mass, times our analogy for speed, angular velocity, 1/2 I omega squared. We'll get to that, but actually just in a few days. And we'll add that to our forms of energy when we take the conservation of energy. So this is nothing, we're not changing anything new, making anything new, we're just adding a form of energy to our list. Finally, and this will actually be in chapter 10, everything else so far is in chapter 9, the last thing we did with mechanics is we looked at momentum, and we're going to do the same thing here. The difference here is that we're actually going to learn about a whole new quantity called angular momentum. And angular momentum, this is what's potentially confusing, and that is that with energy, rotational kinetic energy is actually just plain old kinetic energy. It's measured in joules, and joules, it's just kinetic energy appearing differently, if you will. Angular momentum is a whole new quantity, different quantity from anything we've learned before. So it's not the same thing as angular momentum. In fact, it's angular momentum with another term thrown on, kind of. Don't worry about it for right now. We'll get to it. But the point is that this is a new conserved quantity. And it's another very powerful idea, the idea that an isolated system has a constant angular momentum, and that allows you to do neat problems. One of the classic examples of this is a figure skater who's rotating and pulls in her arms and legs, or his arms and legs, and spins faster. And lots of athletes that rotate do this. If you pull your arms and legs in, you spin faster, and that's because that happens to actually preserve the amount of angular momentum that you have. You change how your mass is distributed, it actually makes you spin faster or slower, and as I say, that preserves the angular momentum. That turns out to be a nice example of conservation of angular momentum. So that's going to close out our study of rotation. So basically, here we go. As we study rotation over the next several days, we're going to study kinematics, we're going to study dynamics with torque, we're going to study energy with a new form of kinetic energy, if you will, and then the last thing we'll do is study angular momentum. That's how we're going to organize our study of rotation. So here we go.